you very much for the invitation, and I would like to apologize that I cannot attend all talks, but I will make sure to watch them afterwards. So my title is BCFT at large charge, and it's based on a paper we posted with Gabriel Cuomo and Raviv-Moshe this month. And let me start by a puzzle, and please stop me at any time if there's any question or confusion. I didn't include much of an introduction, since this is an audience who's mostly familiar with what I'm going to be talking about. At least that's what I'm assuming. So the puzzle is how to describe Dirichlet boundary conformal field theory in this large charge approach, in the large charge effective field theory approach. So the context in which I'm asking this question is that we have learned that there is this nice large charge EFT in the bulk based on a constant degree of freedom chi. The leading action is d chi to the d power times some Wilson coefficient, dimensionless, and the current, the U1 current, is obtained from Noether procedure by taking the d mu chi derivative of this Lagrangian, and takes this form, so contains this d chi to a fraction to some funny power times d mu chi. And so let's just review how this EFT arises in a controlled setup in classical field theory and classical phi-6 model in 3 dimensions. So here's the Lagrangian in mostly minus signature. And okay, so at finite chemical potential, turning on chemical potential, it's advantageous to introduce polar coordinates in field space. So rho will be the magnitude of the field, and chi its phase. And at finite chemical potential, this chi, this phase rotates quickly, mu times t, and then there are fluctuations, which I denote by pi throughout the talk. If we do this change of variables, then we get 1/2 d rho squared. Then there is a chi kinetic term multiplied by rho squared, and some rho potential. Okay, and the current is rho squared times d mu chi. Okay, so now let's try to put boundary conditions. We know what boundary conditions mean in the UV theory, and then we'll try to figure out what they mean in the CFT. So Neumann boundary conditions just say that the z derivative, z being the transverse coordinate perpendicular to the boundary, so the z derivative of rho, the magnitude at the boundary, and also the z component of the current are equal to 0. Whereas Dirichlet boundary conditions would mean that rho, the magnitude of the field, is 0, and that implies through this equation that all components of the current vanish at the boundary. Okay, so how do we implement these boundary conditions in the EFT? Now, Neumann is straightforward. We solve for the equation through the equation of motion for rho. It's a constant throughout the bulk, including at the boundary. It's equal to the 1/2 power of d chi independently of z. And so the EFT to leading order is simply the restriction of or integrating the Lagrangian on half space. So for z greater than 0, we integrate the original Lagrangian. And for this example, I'm in 3 dimensions, so d chi cubed. Okay, so that was straightforward. But then when we first started thinking about it, we considered the other example, the Dirichlet boundary condition, and that will pose a puzzle. So in the microscopic theory, if you impose Dirichlet boundary conditions and also turn on a chemical potential, you will find that this field rho has a non-trivial profile. So this is where the boundary is, and this is the bulk of the spacetime. And we have a domain wall whose characteristic scale is 1 over mu. Far away from the wall, the value of rho is the same that we encounter in without the boundary or in the case of Neumann. But close to the wall, there's some profile. Okay, so how do we impose this boundary condition? So in the microscopic description, we saw that, oops, I don't know what happened. We saw that at the wall, all components of the current vanish. Okay, so maybe that's what we have to do in the EFT. But if we impose that in the EFT, all components of the current vanish, that forbids a non-trivial profile for chi, and we know that far away from the wall, we want chi to be proportional to time, mu times time. So that's no good. So this was the original puzzle, and then we tried to come up with some better answers. First idea was that maybe we have to couple this theory to some boundary degrees of freedom that will somehow impose that the charge density has to go to 0 at the boundary. That didn't bear any fruits. So the way out is to concentrate on what we really want to capture through the CFT. We want to be able to compute physical observables that are in the EFT regime, and which we then match to whatever answers we get from the UV. Okay, so one simple observable would be the charge in a box that extends from the boundary to some value L in the bulk. So the way we obtain that in the UV theory is simply by integrating the charge density from 0 to L in Z. Okay, so if we do that computation, we get an extensive term whose coefficient is mu squared. Then we get a subleading in the large L expansion subleading term, which is linear in mu, independent of L, and it has a coefficient that I will call B over square root 8 for convenience. And then the only corrections to it are exponentially small in L times mu. Okay. So this constant contribution, constant in the sense that it doesn't depend on L, can be reproduced from a boundary contribution to the EFT charge density. So if we want to obtain the same answer, if we want to obtain the same answer, then we want to integrate the CFT charge density from 0 to L and get the same answer. Okay, so that we will achieve through a boundary contribution to the EFT current, and I think it's an interesting challenge to also try to reproduce these exponentially small corrections. I don't know if they can be captured in the EFT language or not.
Mark, just one quick thing. When you say that you compute that from the J naught in the UV, which action are you using exactly?
I'm using the UV action, so this one that I wrote.
The 5 to the 6, and you're assuming a flat profile in there. So you just put in chi equals mu t and see what happens.
Yeah, chi equals mu t is a solution of the equation of motion.
Okay.
Yeah, so that's what I'm using. Yeah.
Okay. Thank you.
Yes. Okay, so if we want a boundary contribution to the charge density, then we need a boundary term in the action. And the natural thing that we can write down, which is Weyl invariant, is simply a boundary action of the same kind. So d chi squared on the boundary, and the boundary coordinates I will always denote by hat, or any boundary quantity I will always denote by hat. So this would be the superfluid action or EFT action in 2 dimensions that we would write down. And so this is, of course, valid. Okay, so this is the proposal. You see this coefficient B appearing here, which shows up here as well. And indeed, if we do the Noether procedure for this action, we get a contribution to the charge or to the EFT current of this sort. And if we integrate the 0th component of this for this chi profile that Domenico asked about, the mu T1, then we indeed reproduce this UV answer. So this is one quantity matched with one fudging of coefficients, but we check that other quantities computed from the UV are reproduced through this boundary action. A particularly nice one is computing the phase shift in a scattering experiment where we send in a Goldstone wave. So that's pi incident, and then there's an outgoing wave. There's a phase shift e to the I delta between the two. You can compute it in the UV. Yeah, you can compute it in the IR. And they both give the same answer. There's again this coefficient B, and then it's multiplied by K, the wave vector, divided by mu. So at low energies, this is controlled. It's a small number, and the UV and IR and EFT computations match. So maybe I should have said this before, but this boundary condition for the EFT is for a UV Dirichlet condition is actually a perturbed Neumann condition. So to first approximation, the Goldstone field, the transverse derivative of the Goldstone field is 0, and from this boundary contribution we get a small correction, which is suppressed by inverse powers of mu. So this is what we get. So at leading order it's 0, and at subleading order at order k squared over mu, it's some small thing. So what we learn is that the EFT, no matter what UV boundary condition we put, is basically gonna be Neumann plus some small corrections at higher derivative orders. So this concludes my introduction through this puzzle. Is there any question about this setup?
Okay, I have another question. You've drawn before a cartoon of what you expect the density to look like, right? That is 0 at the boundary, then it goes up, and then can you actually reproduce that with the action that you have written?
No, so that's a very good question. So the EFT is not resolving distances of order 1 over mu. So the important thing was that this is not an order 1 distance from the boundary. This is an order 1 over mu distance from the boundary. So all that the EFT sees is kind of a delta function, you know, a chain or like a cartoon of what the true UV profile is. So that gets coarse-grained, and the only thing that we see is that at the boundary there's a contribution to the current.
Okay.
But the exact details of the profile are encoded in exponentially small corrections to the EFT answer, and I don't know how to, whether even I should aspire to include or to reproduce those from EFT, or that's outside the framework.
Okay, I understand. Thank you.
Any other question? Okay, if not, I can now give you the outline of the rest of the talk. So basically, this was the most interesting finding, or most
Mark,
surprising.
But you can probably find boundary conditions which would require degrees of freedom on the boundary, or you can rule that out somehow.
Yeah. So okay. So here's the outline, and that will answer Zohar's question. So in this framework, I will present predictions for the dimensions of boundary scaling operators, and so that will be the next part of the talk, and then we will verify these EFT arguments through explicit computations in the O2 model in the 4 minus epsilon expansion, and then I would really like to open the floor to discussions on other bulk and boundary large charge phases. And so yes, there are situations where you need extra boundary degrees of freedom in this framework, or I believe even there also exist other large charge regimes of CFTs where you need to use completely different EFTs. So I would put that in the same bracket. So what I presented is the correct story for many CFTs, but not all. And in some cases, you need boundary degrees of freedom. One example, just to preview, is if you can imagine a situation in which the bulk doesn't have a symmetry, but the boundary has a symmetry, and in that case, you need charge degrees of freedom on the boundary. Okay, so we will need just a very few notions of boundary conformal field theory. So this won't even be a lightning review of BCFT. I hope everybody has seen at least some examples of BCFTs, but if something is unclear, please ask. So in BCFT, besides the bulk operators, we also have boundary local operators with well-defined scaling dimension. So I will denote these operators by O hat and their dimension by delta hat. And just like for bulk CFTs, for boundary CFT, we also have a state operator correspondence, which is easy to see. So if I have a wall here, and I have a boundary operator inserted at the origin, and the polar coordinates adapted to this insertion, then by Wahl transformation, I can go to the hemisphere times time. And so operators in BCFT, boundary operators, correspond to states of the theory quantized on the hemisphere. So just like in the bulk case, we will use the EFT to predict their dimensions from computing their energies on the hemisphere time. So let's quickly go through how this computation goes in the bulk, because it will be completely analogous here. So fractional dimensions, fractional powers of the charge come from, basically their origin is the relation between mu, or r times mu, where r is the radius of the cylinder, and q, which simply comes from dimensional analysis. So this is the equation of the state of the superfluid. And then we get the classical contribution to the scaling dimension by evaluating the on-shell action. It starts as mu to the d, coming from d chi to the d. And then from higher derivative terms, we have mu to the d minus 2, and so on. If we plug in this relation into this on-shell action, we get the final answer. Alpha 1, alpha 2 are simply related to Wilson coefficients in the original action. And so we get these intriguing fractional powers, q to the d over d minus 1, q to the d over 2 divided by d minus 1, and so on. So this is the classical contribution to the scaling dimension. It turns out that it's very interesting to look at the one loop contribution, because we'll find universality there. And at one loop, the Casimir energy is simply computed from summing up the 0-point energies of the Goldstone fluctuations. The frequencies I denote by omega L, their degeneracies by NL. These omega L frequencies are obtained by solving the equation of motion, linearized equations of motion for the fluctuations. And this prefactor is just the speed of sound, which may be somewhat unfamiliar compared to equations of motion that we usually consider. Okay, so already in the first paper on famous paper on this, it was noticed that the leading piece in odd dimension is a constant, and that's a universal prediction of the EFT, because there is no operator in the action that can change its value. But until recently, it was not noticed that even in even D, we have a universal prediction. Gabriel nicely showed that we got a log Q contribution in even dimension from this one loop. And so the prediction for the scaling dimension of bulk operators is obtained by adding up the classical and one loop and higher loop contributions. And the highlight of this is that there are universal constant or logarithmic contributions in odd and even dimensions respectively. So how does the story go in BCFT? So here I just copied the same formulas that I used in the bot, and then we will see what corrections we get from, or what changes we get from the presence of the boundary. So if we just use thermodynamic extensivity reasoning, then it's easy to see that the relation between the chemical potential and the charge was changed as follows. So if we had the full sphere instead of the hemisphere, we would have 2 times the charge that we have. And so here's a factor of 2. That's somewhat trivial. The non-trivial thing is that from the boundary contribution to the charge density, we get a shift here. So this number B shows up. Okay. Now, if we evaluate the on-shell action, then we have the 1/2 from integrating over only the hemisphere, not the full sphere, compared to the bulk case. From the boundary term in the action, we get the B times mu to the D minus 1. It's D minus 1 because it's in 1 lower dimensions. And again, at subleading order, we get the 1/2. Okay, so what does this give us in the end? We get the 1/2 from this 1/2, and we get 2's next to each Q. Okay, 1/2 here. From this guy, we get the linear in Q correction. So no fractional powers there to Q. And that this subleading order, besides this 1/2 of a 2, we also get some correction from here, from the relation between the chemical potential and the charge, which is some number which I won't write down. times b squared. So that's coming from this. Okay, so this is the classical contribution. It involves just inserting some trivial factors of 2 and keeping track of everything. But the important thing is that we get this linear correction from the boundary term. Okay, what do we do at one loop? At one loop, if I put a hat on this quantity, again, we have to sum over 0-point fluctuations. The equation of motion for Goldstone fluctuations is the same since to this order, since we are working with just the same bulk equation with some boundary conditions. But the degeneracy is different. We only have to take into account modes that obey the boundary conditions, which are Neumann to this order, and there are small corrections to that, but that doesn't contribute to this order. Okay, so in even dimensions, we get the 1/2. That's boring, but surprisingly, perhaps in odd dimensions, we get again a logarithmic contribution. In stark distinction to what we saw in the bulk. Okay, so what's the raison d'etre for this log term in odd D? So the logic for finding this log Q term, or the physical reason for its existence, is that in the action there exists an operator that renormalizes the order Q to the 0 term, and so from there we are allowed to have a divergence, and we indeed do have one. And so in 4 dimensions, there's a bulk operator written here for the experts. So in terms of the Wahl covariantized metric, d chi squared times the physical metric. So it's square root g tilde times the Ricci tilde square. You can write this out in terms of chi, but I won't bother with that. So that's what Gabriel found in the bulk. But for example, in 3 dimensions with a boundary, we again have an operator, this time a boundary operator, which takes the form of g tilde hat. That means g hat Wahl covariantized times r tilde restricted to the boundary. So this is a term that would contribute to order Q to the 0. It can have a divergent coefficient, and so it causes a logarithmic, or it leads to a logarithmic correction in the one loop Casimir energy. And if you do the computation in an actual setup, then you can see this, and you indeed find this.
Mark, I forgot how that works, given that r hat is a total derivative.
This is not r hat. So this is just r tilde restricted to the boundary.
But isn't the Ricci scalar a total derivative?
Not the bulk Ricci scalar restricted to the boundary. No.
Okay. It's not made out of the induced metric.
Yeah, it's not made out of the induced metric. Yeah.
Okay, thanks.
So, okay, in summary, we get that to leading order, the dimension of the bulk scaling operator, lowest bulk scaling operator with charge Q is 1/2 times the charge of the, or times the dimension of the bulk operator of charge 2Q. And there's the linear correction that I talked about, which is minus some number times B times Q. And then there's this log term in all dimensions that I talked about.
Just one thing, shouldn't you also have the Q to the 0 term added here for odd dimensions?
Yes, but since there is a log term, I chose to focus on.
Okay, no, okay. I was just keeping the counting.
Yes, yeah. I was not careful with what's inside the log, so that's why I chose not to. Yes, there is. Maybe one thought that you might contemplate is whether there is some sign constraint on this coefficient b, and you would be encouraged if you just studied classical examples in all cases that we studied with Dirichlet boundary condition. B turns out to be negative, so that leads to a positive correction here. But then going on, we analyze quantum mechanically examples, and B turns out to be sign indefinite. Okay, so that's just a comment. Another comment is that you can use the EFT, as was shown in many nice papers, to compute not just scaling dimensions, but also endpoint functions. In CFT, it's enough to calculate 3-point functions. For example, we can compute boundary OP coefficients. So we take in the half cylinder picture a matrix element between a large Q state with a little bit more charge, and a light operator of charge little q and dimension little delta. And from just scaling arguments, the answer will go as q to the little delta divided by d-1. There's a distinguished operator in BCFT called the displacement operator. That is the unique scalar that appears in the boundary OPE of the stress tensor. So if we take the box stress tensor towards the boundary, then we get this displacement operator. And so it plays a very important role in the study of BCFT. We can compute its OP coefficient with this charge Q state. It's analogous to the stress tensor matrix element in the box CFT, and we get the same alpha 1 with some coefficient times 2q to the d over d-1, and we computed this number here. I won't write it down. So this is what the EFT can do for you. At least this is what we've done with it. Maybe there are other applications that you can think of. So one nice check on this picture is to actually do computations in a UV theory and see how they are reproduced in EFT. And this is possible thanks to contributions of many of the audience members. So we did this in the O2 model in 4-epsilon dimension. So let me remind you that what you do there is a double scaling limit. You take epsilon to 0, just like you do in usual Wilson-Fisher philosophy, but at the same time take q to infinity with epsilon q, the product of them, fixed. That's why I call it the double scaling. And this was done in Badel et al. And they will show that you can compute for all values of epsilon q using semi-classics. At small epsilon q, you can match diagrams. At large epsilon q, you can match to the EFT. And similar situation arises in the OM model, where you can do n to infinity, q to infinity, their ratio fixed, as was shown by Alvarez Gomez and Susanne and Domenico. I would like to just mention another example, which looks very similar to the 1/n expansion in the OM model, but actually for this EFT is different and somewhat less explored, I would say, which is U1 gauge theory with NF flavors, where you take NF to be large. So here the EFT description already applies in the NF goes to infinity limit with Q kept order 1 but large. And why it applies was explained in a nice paper by Gabriel et al. And it was verified. The EFT predictions were verified in 2 nice papers in the CPM model by De La Fuente. And very recently, there was a condensed matter paper confirming it in QED, so fermionic matter for monopole operators. So it just enlarges the regime of applicability of this EFT method to these gauge theories, which I find that quite interesting and exciting development. Okay, so let me just very quickly go through these checks that we've done, since it's a very nice confirmation of the picture. So what one does here is obtain these scaling dimensions in the double scaling limit. And first, let me just write down what we get in the bulk. So we get, okay, I didn't say, okay, so this is the action that we are looking at. So there's a conformal mass term, 5 to the 4 interaction with some coefficient lambda naught, and then in the fixed point, this is order epsilon, so small. And we get the following expression for the scaling dimension in this double scaling expansion. So we get non-trivial functions f I of lambda star times q, or epsilon q. The leading piece goes as 1 over epsilon, and then there are subleading orders in the epsilon expansion, and similar results apply for boundary scaling dimensions, which are computed by setting up some large Q state evolving in Euclidean time for a long time extent, and then extracting the scaling dimension from by a semi-classical approximation of the left-hand side. This is the same as the original EFT philosophy. Maybe okay. Let me just include a little bit of details, and then we will go on. So how do we do this? How do we set up this contribution? Computation. Sorry. So the way way to do that is to add a term like this to the UV action. This will enforce that we are in the charge Q sector. So we have this is a total derivative term. So we have chi dot. If you integrate it in time, then you get the boundary value of chi at minus capital T over 2 and plus capital T over 2 times Q, and this imposes that you are in the charge Q sector, and we want the saddle point to be this. The I factor just comes from the fact that we are working in Euclidean. So we again do a change of coordinates in field space to rho and in the phase chi, and we look for a time independent saddle point of rho. It solves a nonlinear ODE with the constraint that the integral of the charge density is equal to Q. So you may remember that the current went as rho squared. Okay, so these are just technicalities. In the case of Bach CFT, you integrate over the whole sphere. In the case of boundary CFT, you integrate over the hemisphere. So again, in the Neumann case, we get the trivial profile constant throughout the hemisphere. The hatted version of these non-trivial scaling functions take the following form. The classical piece is just 1/2 times the bulk result, where again there's this factor of 2 for Q, but the one loop piece is very different. Again, it just, I mean, the formula is the same, but the answer will be very different since we only sum over modes that satisfy the Neumann boundary conditions. In the paper, you can see a very detailed analysis of this. It was pretty technical, but we are happy that we managed to do it. So this sum is divergent. We have to renormalize it and then we are left with a finite sum. You have to analyze that finite sum. Okay, for lambda star times Q, a lot smaller than 1, we matched diagrams. We did a one loop calculation, and the answers agree. So this is the bulk result, and this is the boundary result. You get epsilon times Q squared, and the linear in Q correction. Okay, I don't have time to discuss this in detail. And in the large lambda star times Q, so large epsilon times Q limit, we reproduce the FT results with Wilson coefficients that are order 1/epsilon. The origin of these is that in the general analysis, one sees that the leading piece will go as 1/epsilon. For that, you need Wilson coefficients that are large. So they have an epsilon expansion, where leading term is order epsilon. In Neumann, in the classical analysis, in the introduction, we saw that we didn't need this boundary term. So the order 1/epsilon term is absent for B, but it gets generated quantum mechanically. And we calculated it. Here are some digits. And this implies that in Neumann quantum mechanically, we get a small charge accumulation near the boundary. This is a purely quantum mechanical effect that in classical level, we got 0. And note that it's not just that we compute an answer and then we use as many coefficients as we get terms to match. There are very non-trivial relations implied by the EFT, and those are all satisfied in this calculation. So this is also not just that that we can reproduce. It's a check on the EFT framework, but this was already a check. There's no novelty in terms of philosophy. This was already done in the bulk case, but it also works in the boundary case with this boundary action that we talked about. In the Dirichlet case, just like in the intro, rho has a non-trivial profile. In the small lambda times Q limit, we can find the profile perturbatively, and we did this to very high order, and it matches to loop calculations. In the large lambda Q limit, the profile can be found in matched asymptotic series expansion, and the value of B can be found. And in the Dirichlet case, you see that it's order 1/epsilon, just like in the intro. Okay, so with this I conclude the discussion of these checks in the O2 model. Is there any question about this? I know this was a bit rushed and technical, but maybe there are still questions. Okay, if not, I really wanted some time to discuss with you on other bulk and boundary large charge phases. So this is something I find fascinating. I haven't done much about it, but I would like to. So the question that motivates this is how universal is this large charge EFT that all of us have been looking at. Now, we know in condensed matter, there's a plethora of other zero temperature finite chemical potential phases besides the ubiquitous superfluid and superconductor. The first example of such a phase that we learn about is the Bose-Einstein condensate. And I would say that maybe we won't agree, but the free scalar and the sufficiently supersymmetric examples, I like to think about that EFT, which is not identical to the superfluid EFT as describing a Bose-Einstein condensate. Now in condensed matter, Bose-Einstein condensate becomes a superfluid once we add interactions, so it's not very stable under addition of interactions. And okay, so that's that. But in condensed matter, Fermi liquids are extremely important and ubiquitous. We know that it is realized in the case of free fermion CFTs, but are there other CFTs where Fermi liquids are relevant? And Fermi liquids in non-relativistic condensed matter is extremely robust under the addition of interactions. So that might indicate or might not indicate that it should play an important role in large charge CFTs. So we want to ask what happens in the relativistic and conformal case. And there are conflicting intuitions here, and I don't know which one is the correct one. On the one hand, we would say that it should be possible to use Fermi liquids to describe some large charge phases of CFTs, since for free fermion it already works. Okay. On the other hand, there's a very nice series of work by Rothstein and Srivastava, where they show that Fermi liquids are actually impossible in a very analogous situation, which is non-relativistic conformal. So Fermi liquids with non-relativistic conformal symmetry, called the Schrödinger symmetry, are impossible because they cannot, Fermi liquids cannot realize Schrödinger algebra non-linearly. Okay, so the question here is whether you can construct interacting conformal, relativistic conformal Fermi liquids or not. Question, yeah.
Sorry, wouldn't these large and Chern-Simons matter theories be an example of Fermi liquids? Explicitly at large, and I think there were papers by Sun and Shiraz Minwala and people that demonstrated that.
But we need a large charge operator. So you're thinking that those phases would actually describe, like if you put the theory on a cylinder,
right?
And you think they are. So I don't know the answer. Honestly, I initially thought that the example where you have U1 with no Chern-Simons level, with NF fermions, that somehow that wouldn't be described by superfluids, but actually they are. So, but maybe you know more about this. Yeah.
I'm not aware of what to do with when they're put on a sphere, but at least in flat space, I think it's known that they're Fermi liquids. But yeah, that's a good point. I'm not sure if that survives on a sphere.
Okay. Yeah, so there still remains a question whether they are free Fermi liquids or interacting Fermi liquids.
Right, that makes sense.
We know that yeah, but I agree that that's a very promising candidate. I haven't thought enough about it, but yeah, it could very well be that that's the best example to study first.
Right. Thanks.
Okay, so in condensed matter, there's also lots of non-Fermi liquid phases, but they are not very well understood. So maybe that's less promising for us. But maybe they still arise in our CFTs. There are just less technology to analyze them. And another intriguing example, at least to me, is the example coming from holography, extremal Reiser-Nordström black holes. Now I know that in one part of the literature, they are widely believed to be unstable. But at least in my opinion, the arguments for their instability are very weak. On the other hand, there in recent years, particularly I put some citations here. There has been a lot of progress in developing an EFT for these from the gravitational perspective. This is the famous Schwarzian theory, and if we are thinking about RM black holes in ADS4, then these get decorated by a U1 and an SO3 gauge theory. Those are somewhat trivial compared to the Schwarzian. So Schwarzian is a quantum mechanical model. The superfluid EFTs that we've been thinking about are quantum field theories. So the analogy is with just keeping the zero mode of the Goldstone field in our setup. So if you just keep that, that would be the analog of the Schwarzian. So what can these be used for? One thing that we can do is compute heavy light correlation 4-point function with this Schwarzian. So what we get is initially a 2-point function that just depends on time, but it's a 2-point function of light operators which are labeled by this actual additional spin label. These are obtained by KK reducing these light operators on the sphere. So this is the output, and then we can reconstruct a 4-point function from this by summing over, so this is obtained in, let's say, in some microcanonical window for the heavy states. This is the FT answer, and we can get the full approximate CFT 4-point function by simply multiplying by Gegenbaur polynomials and summing over all spins. Okay, so why did I write down this random formula? Because this same correlation function, heavy light, was analyzed by Jeffries et al. In a bootstrap approach, and it was shown that the superfluid EFT satisfies crossing between S and U channels in very non-trivially. And so the hope, and we, in another paper with Zohar and Avia and Sridip, we analyzed the constraints coming from similar correlation functions for large charge EFTs or large charge limits of CFTs. And so I'm thinking that analyzing crossing for this object, what you get from the gravity analysis could be fruitful. First of all, checking if it satisfies crossing. Secondly, how, if yes, which is the likely answer, then whether it's a trivial mechanism or a non-trivial mechanism. And this is what I'm currently doing with 2 students in Stony Brook, Hare Krishna and Misha Litvinov. Okay. So finally, in this paper of Jeffries et al. That I mentioned, by analyzing their bootstrap equations, they found many strongly coupled solutions of the bootstrap equations, which are not the large charge EFT. It's an interesting question whether there are any CFTs that realize this solution of the crossing. Now, so this was bulk CFT. BCFTs are even richer. And in this paper, we found many situations. Zohar's question already anticipated this, where we have controlled examples where the superfluid is not the right description. One one case is when we have a free box scalar, but with an interacting boundary. So here is a free box scalar and a phi to the 4 interacting boundary. We analyze this in the epsilon expansion. In the small lambda q regime, you just get small corrections to q times the naive engineering dimension of the phi field for the scaling dimension of boundary operators, but in the large lambda q regime, the coefficient here changes to b over 2. That's one result. There are also free fermion BCFTs. For free fermions, there are 2 conformal boundary conditions. For both of them, we get that the boundary scaling dimension is 1/2 times the bulk scaling dimension at twice the charge. And we also found some very exotic examples where we have a neutral bulk, but a charged boundary. In this case, so you would expect that you get a superfluid only in the boundary. And that's true to some extent. So we get a boundary superfluid, but it induces some funny boundary conditions for the bulk CFT. And so the EFT description is turns out to be some kind of hybrid. You get a strongly coupled bulk CFT, a boundary superfluid, and they are coupled through an irrelevant interaction between boundary operators so boundary operators in the strongly coupled theory and the superfluid. I didn't want to specify too many details. I'm just showing you that you can find something exotic here as well, and which is somewhat controlled. Of course, to do computations in this is very challenging because you have a strongly interacting component even in the large charge limit. Okay, so with this, I would like to thank you very much.